Here we go. Okay, so we have Joshua Gutow giving us Introduction to Architecture. Josh, welcome. Thank you so much for being here. I'll let you take it away.
Awesome. Let's see, can I get my slides up? Okay, slides up. Cool. Awesome. Hello, everyone. My name is Joshua, and I'm going to be talking about Introduction to Architecture. This is actually a little less architecture in terms of buildings and cool shapes in the sky, but this is going to be about software architecture. And then more specifically, Bedrock's architecture. And as Carl was talking about the various components of the OP stack, this is going to really highlight how Bedrock, the system, fits together and all of the different pieces there. Cool. So the introduction. So today I'm going to be talking about what even is Optimism Bedrock. Carl's talked on that, but I'll expand on that a little bit more. I'm going to give an overview of the system, both of kind of like the components and also the actors. So we have a bunch of different pieces, but some of them do different things. Then we'll go through the rollup node, which is one of the components, the sequencer and the batcher. Then the proposer fault-proof challenge agent, so that's all of the stuff that enables withdrawals. We'll go through a couple data flows, and then go through some kind of final implementation notes at the end. So, what even is Optimism Bedrock? Bedrock is a network upgrade to reduce fees and increase implementation simplicity. So I'll kind of go through a little bit word by word because it's a big complex sentence with a lot underneath of it. So network upgrade. So Bedrock is going to be kind of a point in time release. The thing we'll have, like, we have our current system, we'll have the Bedrock release, and then we'll have more releases in the future. So the network is still Optimism. This is just the network upgrade. And as part of a network upgrade, we'll be keeping all of the history with the Optimism network. This is just one more step in improving the user experience. And specifically, the biggest change to the user experience is going to be reduced fees. And then the non-changes to the user experience are going to be increased implementation simplicity. This is something that most users won't see, but really improves the performance, improves the reliability, enables a lot of other things down the line. So how do we get there? Bedrock achieves this by redesigning the rollup architecture. So a lot of the things from the previous system kind of are getting modified, and then we're drawing a lot of like new lines between different components inside the system and really making sure that everything fits together in a way we're happy with, and also in a way that kind of enables different components to be swapped in, swapped out, how components can be tested by themselves, and making sure that everything fits together very neatly. So now we get into the fun part, which is the architecture. So we're going to go through the system overview. So here's kind of the discrete components. You have a rollup node. This is OP node, and then there's the execution engine, OP-geth. We put OP in front of everything because why not? The batcher is the OP batcher. The proposer is OP proposer, and then we don't have a challenge agent, and the fault proof is canon. So OP node and OP-geth are kind of the things that produce blocks, and that's like your full node on Ethereum. OP batcher submits L2 transactions to L1. Then the proposer submits output routes, and this is what enables withdrawals. And then we talked a little bit about canon, and have talked more about canon in the past, but that is the fault-proof system. And the challenge agent is just a simple agent that interacts with the fault-proof system. Cool. So those are different code bases and components. How do they translate to the actors? So the actor is someone running, so you can run a multiple code base lots of times. So verifiers, that's a full node. So there's going to be a lot of those. That's just like running your full node on Ethereum. And that's to do that, you need your OP node, which is like your consensus client, as well as your OP-Geth, which is your execution client. Then you have the sequencer, which is a full node that is mining, and so it produces blocks, and then it also gossips them out and does a couple small things, but under the hood, it's very similar to the verifiers. And then you have your batcher, which is an actor that just maps straight back to the code base. Same with your proposer, and then your challenge agents as well. The sequencer and verifiers actually have to map to a couple code bases because they're more complex things. So, giant diagram time. So this is going through how all of these actors interact. So if you want to kind of deposit into the system, we'll just follow that execution flow. So the user sends a deposit transaction to layer 1, and then the sequencer reads the deposit. Sequencer also then gets transactions kind of separately. Then it creates the new blocks, sequences them. The batcher then picks, and that's kind of how you get deposits. Now, once you have your L2 transactions included, a user sends them to the verifier, they get to the sequencer, you create your blocks, the batcher submits the batches. Now then the verifier reads both the deposit and the batches, and then it derives a chain that matches the sequencer. And so that's kind of the transaction flow. There's a lot of moving parts here, but that's kind of what it is. And we'll go through some of these flows in a little more depth later on. And then when you're doing output proposals, the output proposer reads the state root from the verifier and then just submits it to L1. And that's the OP proposer. And then the challenge agent would interact, would kind of use the verifier, again, looking at the state root and comparing it against what got submitted on L1. And so it's reading between the verifier and L1. And those are, again, all the system actors and how they interact. Cool. So time to dig deep into the rollup node. So it does several things. Reads data from L1, has both deposits and batches. As Carl mentioned, it uses the L2, the engine API, to talk to kind of the execution client, OP-Geth. There's a P2P network, and I'll talk a bit more about that later. And then just as an implementation, it's way simpler than the current L2 Geth implementation. It's a lot closer to upstream, and it's a lot easier to work with. So the diagram. So this is basically all of the components that you need to run a replica or a sequencer. Just a node on Optimism, a full node on the Optimism network. So on the Ethereum side, you have your consensus client and your execution client. They talk to each other using the engine API. And then your OP node, which mirrors the consensus client, uses just your standard ETH JSON RPC. So it does stuff like gets blocks, gets transactions, gets transaction receipts, just kind of essentially reading in the chain data from L1. And then it talks to the L2 execution API, L2 execution engine through a very slightly modified engine API. It's very similar, but I'll talk through a couple of modifications there. And then the OP-Geth or L2-Geth is a small diff on top of Geth. It's actually a little larger than 500 lines right now, but not really that much more. And so that's a lot easier to work with and keep the OP-Geth up to date with upstream, so we can bring in a lot of those improvements a lot faster than if we had done a lot more modifications to that. And so this is a single node. So now what happens when you have multiple of these nodes? So this is where every node is talking to almost every other node. So the vertical lines there basically maps back to the previous diagram, and horizontal lines map back to the previous diagram. And so the top line and the bottom line are two different sets of nodes. So on the left here, you have different consensus clients for Ethereum talking to each other through the beacon chain. Then L1 clients on Ethereum have a sync protocol. They have a transaction pool. And then on the L2 side, we gossip out L2 blocks for the OP node, and then we actually use a lot of the same sync mechanisms, transaction pools, all of that when L2 execution engines are talking to each other. So getting into the details of this engine API, which is what connects the OP node to OP Geth. It has two extensions, and these extensions are to some of the payload attributes or like fields. So we have two more fields when we're calling fork choice update, but the rest of it's basically the same. And the engine API is actually really simple. There's 4 calls, one of which we don't use at all because we don't have a transition, so it's just not relevant. To the new payload call is just insert a new block into the execution layer. Simple. Fork choice update is a little more complex because it does 2 things at once. It sets a head block, including kind of safe and finalized blocks. And it also, if you give it an optional parameter, it starts the block building process and it returns back kind of reference to that in-flight block. And if you want to get that in-flight block that it's building, you just call get payload. And that's basically it. This is pretty standard API. It's specified by Ethereum, and it makes it really easy to include new execution clients. OP Aragon, that's not that much work to port over 1,000-line diff. And then eventually, we only have one rollup node right now, but it wouldn't be that hard to create a new rollup node that spoke this API and worked with any execution engine. So deposits and batches. So we've briefly spoken about deposits as kind of a way to get money into L2. These are going to be a lot faster now because we're reading them a lot closer to the chain tip. But they also serve another purpose. And the sequencer basically cannot delay deposits outside of a certain range and has to eventually include them. If you're interested in more details about the specifics of how this works, I gave a talk at ETHCC that does a really deep dive into Bedrock and goes through all of this and why this is true. But the net result of this is that the chain advances even if the sequencer doesn't want it to. And then this enables censorship resistance. And then if you never had a sequencer again, you could still unwind the chain through deposits. So deposits also do a lot more than just mint money on L2. They're fully featured transactions. So anything you can do with a normal transaction, you can do with a deposit. And so typically, you actually wouldn't use deposits that much to do this because deposits just get included on L1 kind of one transaction at a time and actually have some state execution on L1 versus a kind of direct L2 transaction. When we batch those, we take a bunch of those, we compress them, and then we just shove it in call data of L1. So direct L2 transactions tend to be cheaper, and that's kind of the typical flow. But if you need to, deposits are always there. Okay, P2P. So here we kind of described how sequencers gossips out blocks. And so the feature that's enabled here is that if you're just a replica on the network and you're subscribing to these unsafe blocks or blocks that have the sequencer has just created, your view of the network is incredibly up to date. And so you can choose to insert these blocks. Now, as part of kind of inserting these blocks, we don't actually mark these as fully safe because there's no guarantee that the block that you received will kind of get submitted to L1. So we prefer in the rollup node, whatever gets submitted to L1 over what the sequencer says. And kind of as a result of this, it's a very minimal trust assumption to insert these blocks and stay up to sync with the tip of the chain. They have a really good user experience without actually sacrificing trust. And this is kind of a similar thing to the liveness thing, liveness in Ethereum, where you have a head block, which could reorg, but then you have your safe block, which is assumed not to reorg, and then you have your finalized block, which will never reorg. And so we've brought over the same kind of terminology and same usage of the engine API to mark blocks as safe, which are very likely to not reorg, finalized, which will never reorg, and then your head block, which you've got from the sequencer, which is likely to be included, but it could change. And that's kind of the whole P2P subsystem. And then as a part of a result of getting these blocks as they're distributed, it's really easy to hook into a snap sync. It's not yet implemented because you can just re-execute all the blocks, but that's something where this architecture of splitting out the execution engine from the consensus layer, that's something that's really easy to do and something we will be doing in the future. Cool. So we've covered the rollup node, talked about OP-Geth and the OP node, how they interact, and how different nodes interact with each other on the network. And now we're going to talk about the sequencer and the batcher. So what's here is basically talking about the sequencer, which a normal node essentially. It runs a mining process. And then it's like, just like Ethereum, how every full node has mining code in it. It's all like every rollup node will also have mining code in it. And there's just one specific one that can run. And then the batcher is a pretty simple code base, just takes L2 blocks, transforms them to the data that you expect, does compression, that's how you get low fees, and then just submits them onto L1. Easy peasy. And then having that be so easy is basically like small modular architecture. That's a theme here. So now the proposer, fault proofs, and challenge agents. So this is a group of kind of three, which will be at least 3 different code bases and a couple different agents. But what's here is this is everything that's required to enable withdrawals. So the proposer is kind of the entry point into withdrawals. So it reads state from L2 and then puts it onto L1. And then after, if you put it onto L1 and no one says this is invalid, it's then assumed to be valid. That's the optimistic part of our rollup. And that kind of validity then enables withdrawals. And if it's, and if it's not valid, then you go through the challenge game and the fault proof. So it's not yet live. See some canon talks that NorSwap's given for more information about this. But the fault proof is what secures the bridge. This is how you say, if someone submits something that's invalid as a proposer, the fault proof is what marks it as invalid. And we time bound how long you have to say, hey, this is invalid, so you can actually eventually withdraw. But it still needs some amount of time for the finalization period to basically have enough time that no one can censor the chain for long enough with this withdrawal period. So if it's like a 10-second finalization period, you could censor the chain and then get any fake output through. With a week, you can't censor the chain for a week. And then if there's ever an invalid output proposal, it will be caught. And then, so the actual fault-proof game is super fun and exciting, and I'll nerd out a little bit over it. So the entire thing is called Canon, and it has its whole own sub-architecture. It's like a lot of interesting things in there. But it's an interactive proof game over a MIPS execution chase. So like everything here, it's a lot summarized into a short sentence. So the interactive proof game is kind of this binary search-like thing. So you start out with some code, you execute the code, and you can imagine the code is like executing an instruction, like an add, a subtraction, a load from memory. And so what we do is we have kind of an on-chain version of this, and then your 2 off-chain components. The 2 off-chain people both run their execution chase, execution, your challenger and your defender. So the defender is the person that submitted the output proposal, and your challenger is the person that says, no, this is invalid. And at each, you run the execution trace, and you agree on the start and disagree on the end. And then you can kind of Merkleize the state, do some funky things in there, and then basically run a binary search over like, okay, we agree at this step, we disagree at this step, and then you can finally narrow it down to a single instruction execution, and then execute that single instruction on chain. It's super fun, super interesting, and then actually enables you to kind of fault-proof really complex things really easily. So anything that's deterministic and compiles to MIPS can be fault-proven. So the whole derivation process is going to get imported to Cannon. All of the EVM is going to get imported to Cannon, and we'll kind of go through the fault-proof. Any compression we do, again, just straight through. So we don't have to deal with like loading up data. We can load in the raw data that the rollup node uses, which is again just transactions and blocks. And so those are really easy to kind of load up on chain and prove that, hey, this is actually the block hash on chain. And so that's basically all of that. Super fun, super interesting. Not yet live, but we're working a bunch on that. Okay. Getting back here. Okay, so that's how we secure the system. So I'm going to go through some data flows in the system. You'll see how kind of different things interact, and maybe it'll make it a little more concrete. So we'll talk through the deposit, L2 transactions, and we'll also go through withdrawals in a little more detail. So the deposit, you send a transaction to a contract. And the key thing is that the contract does some computation, make sure you pay your fees, make sure you lock up your ETH, and then it emits the event. And that event is what we're looking for on the L2 node. That's the authorization that, yes, you locked up your ETH, yes, all of this is valid. Then the rollup node reads the event, creates a special transaction type on L2, and then we insert these transactions at the start of the block, and then eventually that deposit gets executed on L2. There's a couple more details in there around like gas accounting, but not quite relevant for this talk. So then if you're submitting direct to L2 transaction, you send out your transaction, it gets to the sequencer, and then the sequencer has a set of transactions in kind of its local mempool, and then it creates a block based on that. Then once the sequencer has created its block, the batcher sees, hey, there's a new block. We need to go submit it to L1. So then it takes it, combines it with a bunch of other blocks, does some data transformation, compresses it all, does a little more like data slicing, and then puts it on L1. And then the rollup nodes read all the call data, look for transactions to a specific address, check the authorization on those transactions, and then reassemble the blocks from that submitted data. And then you have, voila, your transaction on L2. Cool, so withdrawals. So withdrawals are a little more complex because you have to manually kind of do the communication across the layers. So to initiate your withdrawal, you send a transaction to L2 to the withdrawal contract. And so the withdrawal contract does several things. It basically creates a commitment to how much you're withdrawing, then burns how much ETH you said you withdraw, emits event to make it easy to index and track it. And then it also touches some L2 state based on kind of the commitment to the withdrawal. And this touching is really important because we'll use that later to verify that you actually burnt your funds on L2 and can kind of withdraw them from the Optimism portal on L1. So after you do this, then you have to wait around for the proposer to say, okay, I've got this new output route. go have the proposer submitted on L1. You have to go through the challenge period to say that no one's making a fake withdrawal. And then finally, you can execute your withdrawal on L1. And so what you're doing there is verifying the withdrawal contract, or the Optimism portal on L1 when you're doing the withdrawal, is verifying that you have a valid proof of your kind of commitment to your withdrawal. So like you have a withdrawal that says, I want 10 ETH back. It says, hey, you actually did have an event or state on L2 that shows that the only way the state could have been true is that if you had actually burnt 10 ETH on L2. So that's like the proof system there. It's basically the overview. There's a couple more details about assembling all of the proofs, but that's kind of mid-level overview, not fully high level. So we have a couple data flows. Let's talk about how it's all assembled. So we've been talking about a bunch of different components, and these are a lot of small modular code bases. So the OP node is about 15,000 lines of code. The OP geth, it's about an extra 1,000 lines of code on top of normal geth. And we find that's kind of what it takes to get another execution engine onto Optimism. The OP batcher and the proposer around 2,000 lines of code. As we kind of get those more production ready, it'll grow a little bit, but it's likely to remain under 5,000. The contracts around the portal, L2 contracts, all of that's around 10,000 lines of code, but that's with all of our tests and supporting code. So none of these are giant, hairy code bases that are all intertangled. They're all kind of off in their own little world. They have clean API boundaries between them, and they're a lot easy to work with, easy to upgrade. And so that's been one of the big pushes with this new architecture. So if you're interested in kind of looking at the code, learning more about it, all of our code is in the Optimism monorepo. We have the OP node codebase, the OP batcher codebase, the OP proposer. Those are just top-level folders. If you want to look at the Bedrock contracts, it's in packages/contracts Bedrock, self-explanatory. And then we have specifications for how the entire system should work inside the specs folder. Cool. So in summary, Bedrock is a network upgrade to reduce fees and increase implementation simplicity. And we basically talked through all of the architecture that enables this. So this was Introduction to Bedrock's Architecture. Again, I'm Joshua Gutow. Find me on Twitter at TriangleSphere. And if you're interested on working with Optimism, or all sorts of positions there, but in particular, we have positions to work on Bedrock. So if this is exciting to you, we're hiring at jobs.optimism.io. Cool. That's it for me. Have a good day, everyone.